We will learn how to code a neural network both from scratch using only NumPy and also using TensorFlow, and we will learn to predict these images of handwritten digits into actual digits. So this is number 4. The AI will predict that this is handwritten number 4. Let's start from top and execute this first line. You can find this notebook in the description below. Maybe you could rewrite this manually, this code, but if you want, you can just follow or rewrite it. And then let's load the data. So we're gonna split into, this is input, this is Y is output. So this is gonna take some time. We're gonna have to convert Y to integer labels, so these are like the outputs, the number 3, 1, 2, 3, 4, 5, 6, etc. And we're gonna need to convert them to integers because that's how our neural network works. And let's normalize the input data. So just to have more stable training, let's put this between 0 and 1 as opposed to 0 and 255. I'm gonna zoom this in a little bit. Now you see how x of 0, how this is between 0 and 1, all of the values of pixels. Now I'm gonna execute this line, which will draw this image on this number. So if I just change this number here, this is gonna be like some other image. So this is gonna be number 5, the first image. The second image is gonna be number 0. And if I remove this CMAP gray, it's gonna display in these colors. So I want to actually keep it as gray. I think this is not important. You can display in colors. This has nothing to do with the training. So this is just the display. And we need to reshape to 28 times 28, because if we don't reshape, then this will just show a line of pixels. Yeah, this is invalid shape. So this won't even show a line. This is just invalid shape. But if I reshape to 784 times 1, then we see this line of pixels. But it should be 28 times 28. Let's now define this stochastic gradient descent optimizer class. So first we're going to have some learning rate. This is just so it makes the values of our updates smaller. So we multiply with this learning rate, which makes it smaller. I will explain later if you don't understand. So let's just set self.learning rate to this learning rate. And then update model parameters based on gradients. So we will calculate gradients later. So this is how AI learns. So we have this update function. We pass in the model parameters and gradients. And then for each parameter and gradient, so this zip is going to cycle through each until the first one is empty. And when the first one, whichever one gets empty first, it's gonna stop cycling. But I think it has equal length, equal size, so it will just cycle through both of them. And then update each parameter by subtracting the product of the learning rate and the gradient. So basically the parameter, we subtract the gradient, but we multiply this with learning rate, so it doesn't subtract too much, so we can slowly learn. Let's take a look at one-hot encoding here. So we have two things here. We have some array that only contains values of 0, 1, and 2, and they can be repeated. And then we have identity matrix. So I will show you what identity matrix is. Let me run this. This is identity matrix. It has ones amongst diagonals. So let's just imagine we have only these 3 rows. So the first element has 1 here, the second element 1 here, and 1 here. Now, what I'm doing here is assigning these values to be basically in the, so I'm taking, for example, the first row of this matrix that has index 0 and replacing this value 0 with corresponding row with this index. So for example, right here, I'm going to take the row with index 2 and replace this value 2 with this row that has index 2. So basically, instead of getting this array of integers, I'm going to get array of these arrays of these. And then, for example, if I want to swap this array with this array, then I would just make number 2 here and number 1 and then run. And now you see that they are swapped. So this is correlating identity matrix rows with these indices. And so if I want to print, for example, the 4th element, which is this one, then I just run this with index 3 and I print this element. Let's see below how clipping works. So if we have some array and you see that I have a very low value here that is smaller than this epsilon value. So when I np.clip and I pass in this array and I pass in lower limit and upper limit. So the upper limit is 1 minus this, so it's going to be 1.95. So everything that's bigger than 1.95, like this one, will get clipped down to 1.95. And everything that's lower, all of these values lower than this, will get clipped to this value, like that. So if I run this, we see that this first value gets clipped. The second value also gets clipped because it's higher. This one also gets clipped, and this one gets clipped. Let's take a look at categorical cross entropy. So this is the loss function, computes the categorical cross entropy loss between true labels and predicted probabilities. So for example, we have some like image of number 3, and obviously the true label should be number 3 with 100% certainty, but maybe our model will say like it's 70% number 3, and then like 20% chance is number 8, and something like that. So we need to compute the difference between the predicted probabilities for this handwritten digit and true, and then return this loss result. To avoid numerical instability when computing the logarithm, we add a small epsilon value to the predicted probability. So this is basically clipping that I explained. What we do is we don't want to get logarithm of 0, so we just add a small value so it's not 0. So here below we do the one-hot encoding. As I explained before, we convert the true labels into one-hot encoded vectors because they will have like it's 100%, for example, number 3, and all of the other digits will have 0% probability. And down below we compute the categorical cross entropy. It's also known as negative log likelihood. So the loss is the negative sum of the true labels multiplied by the logarithm of the predicted probabilities. So we're talking about this, and then the sum of all of these is going to be a negative divided by the number of samples. Intuitively, it gives us a sense of how well the model is doing the predicting of the class labels. And now let's manually code everything. So class simple NNN. It's going to take input size, hidden 1, hidden 2, and output size. So let's create the first weights matrix. It's going to be randomly initiated, and then input size and hidden size times 0.0. This is just to make the training more stable, so there is no like expanding, exploding gradients, exploding values. Just to start with smaller numbers. And then the bias will be at zeros. So we have to put this at zeros because we are adding bias. And this must be random numbers because we are multiplying, so this cannot be initiated at zeros. So it's only 1 in 1 dimension and then hidden size. So for each of the hidden size neurons, we just add this once. And then this is the second weight matrix, hidden size 1 to hidden size 2, same as second bias. Third, from hidden size 2 to output size, and then the third bias. And I also define the optimizers to be our stochastic gradient descent that we defined earlier. Below we see a ReLU activation function. This will just return the maximum between 0 and the z value. So basically this will set values lower than 0 at 0, and then this will just return the values that are greater than 0, will not change them. So we have softmax. So returns probability distribution over all cases. So this is used to predict in the end the probability. So we have digits from 0 to 9, and then this softmax will just convert whatever our results are here in our neurons to like probability distribution. Like for example, it's 90% to be digit 3, 10% to be digit 1, and 0% for other digits, let's say. So let's see, it's here. Subtract the maximum value along each row to prevent overflow. This is a common trick when computing the softmax function. It does not change the result, but helps to avoid overflow. This is where we do it. And then compute the sum of the exponentials along each row. This will be used to normalize the probabilities. And then we will just compute by dividing this value with the sum. Now let's take a look at the forward pass. So first we matrix multiply the inputs with weights 1 and add bias. This is the output, save as to z1. Then we pass that through a ReLU activation function, and then we pass that to the next hidden layer, to the same, and to the next layer. So this is between the middle, the second hidden layer, and the output. And then in the output we just apply softmax, so we get probabilities for each of the digits, and then return A3. So this is going to be array of probabilities. Let's continue with the backward pass. This is back propagation. So we have input data and true labels, and we have output, predicted output. So we will compare the predicted output with the true labels, and we will update the model parameters. So let's see, M is number of, so this is number of training examples. Convert Y to one hot encoded. So Y are the true labels, true data. This is necessary because the output of the network is a probability distribution over all cases, and we need to compare it to the true labels. So I already explained the one hot encoding. And then output layer, calculate the error gradient of the output layer. This is the difference between the predicted output and the true labels. Then calculate the gradients of the weights and the biases of the output layer. These gradients are used to update the weights and biases during back propagation, right here. So we're gonna calculate the error gradient in the second hidden layer, and then we're gonna apply the ReLU activation function to the error gradient. This is necessary because the ReLU function is used in the forward pass. Calculate the gradients of the weights and biases of the second hidden layer, and then calculate it back in the first layer. Apply the ReLU again, and then calculate gradients of the weights and biases in the first hidden layer. What? It's okay, this is gradients of weights and biases in the first hidden layer. And then we're gonna use the optimizer here. Okay, so this is this is the training loop. We have 100 epochs, batch size 32, and then we go through each epoch and we split X and Y. So this is we take the training data for the images, and then these are the labels. We pass it through the forward pass, and then we pass it through the backward pass. And every 10th epoch, we're gonna calculate or show the loss. And then we also define the predict function that lets us just pass through the forward pass and get the probabilities. So I'm gonna run this, it's gonna just save it, and then I'm gonna initialize the model. Input size, this is the input size of the dimensions of the pixels of the image. Hidden size, and then we're gonna reduce it, hidden to size to 64, and then the output size is 10 because we have 10 digits. And then we define this model, and then we start training. So we say 100 epochs. Now this is gonna take around a few minutes, I think. So this is not optimized with like GPU or PyTorch or anything. The training finished. Here we can see that our loss is getting smaller and smaller. So let's go here. In the end, I'm just gonna run this. We see this digit and predicted digit is 3. So let me just change to something else. This is 5. Yeah, and that works. This is just for debugging if it doesn't work for you, but for me it works. Now let's rewrite this. Everything is in PyTorch, so it's gonna be a lot smaller code, a lot smaller piece of code. So first, we're gonna check if we have GPU enabled. So go to runtime, change runtime, and I have GPU, okay. And then we're gonna load dataset, and then split it into training images, testing images, training labels, and testing labels. And then we're gonna convert to tensors and move to GPU, so to device. This device is defined here to be CUDA or CPU. CUDA is GPU. Create data loader for batching. We're gonna just load the data into tensor data with tensor dataset, into train dataset, and train loader. So let's define the simple neural network. This code is a lot smaller, as you can see. And let's compare this to our big class. So it's all of this. Look how big it is. Let's go below again. We see the first linear layer, input size hidden, and then hidden 1 to hidden 2, hidden 2 to output, and then the ReLU. So we don't need to implement any of this logic. It's already implemented in PyTorch. And then the forward pass, we're gonna say the first layer pass through ReLU, the second layer pass through ReLU, and then the third one, this will be the output. We initialize everything same. We can use a criterion to be our cross entropy loss. We don't need to define it manually. And then I'm gonna use Adam instead of stochastic gradient descent. It converges faster and it's better. Training loop, number of epochs 10. I think I put 100, but here I put only 10. But let me see. I think this will also work as well. So this is the same. So we say forward pass, outputs is model pass in batch X, then calculate loss, and then backward pass with optimizer, and that's it. And then evaluation. So if I run this, and now we can go here to test after the training has finished. And this is number 3. Let me replace to like 44 here. That's gonna be number 4. Thank you for watching. Find this notebook below and see you in the next video.